Hello and welcome back to my Physics Online video lecture series. Today's video we're going to be talking about the LR circuit. That's a circuit that has a series combination of an inductor and a resistor. I'm mostly going to be focusing on the, let's call it like the math side of this circuit rather than the graph side. Which may be for a different video. However, I may show a few graphs in this one just to kind of complete things. So, what is the series LR circuit? Basically, what you have is a circuit that has in it an inductor and a resistor. So I'm going to draw a diagram for that. All right, so this gives us basically a circuit that lets us consider the possible cases involved. Essentially what I've got here is an inductor and a resistor in series, and then a switch that can essentially either put them together in series with a battery or simply put them together with a short. So in other words, no battery, but you have a closed circuit. And so the question is kind of what happens if we move the switch to one or the other position. So for example, position 1, our loop rule would look like the battery EMF minus or plus really the voltage drop across the inductor plus the voltage drop across the resistor equals 0. So that's the loop rule for position 1. For position 2, basically no battery present, your loop rule would just look like delta VL plus delta VR equals 0. So now we ask, okay, well, what are delta VL and delta VR? So I've applied the loop rules, but I still have to apply things like Ohm's law and definition for resistance. So Ohm's law, that one obviously just is giving you the voltage drop across the resistor. It should be the current times the resistance. And then for an inductance, inductor, basically we can make use of the fact that the induced EMF, which is essentially your voltage drop across your inductor, should look like negative L times rate change of the current through the inductor. Okay, so we can basically look at these as possibilities. And so going back to the loop rules here, so loop rules again, with battery or loop 1, in other words, you basically have the battery EMF and then you have the current times the resistance. And note that if this is my battery, my current I would expect to basically be doing like this guy. And so this battery's EMF and this current are kind of opposite signs of each other. Down here, for what it's worth, your current would maybe do like this. In any case, they're going to have opposite signs. And then you also have your voltage drop for the inductor, which is negative L delta I over delta T. And all that is 0. And for the second loop, for that one, you actually end up with something like I times R minus L delta I over delta T is equal to 0. Now you may be wondering like why this relative sign change between these two here. Well, in this one, essentially as the battery is plugged in, I expect the current to start like ramping up, and so my current is increasing and it's increasing from 0, so delta I, delta T, and I are basically kind of like same direction. Down here, the current is dying down because you removed the battery from the loop, and so delta I over delta T and I are in opposite directions. Okay, so that explains like the relative signs in these two. In any case, these equations look a lot like the equations for the RC circuit that we got earlier. So recall RC circuit, what we ended up having for our equivalent loop rules, we could call them like 1' and 2' for the equivalent RC circuits. Those ones ended up being essentially epsilon minus IR minus delta V is Q over C, so basically like Q over C is 0. But we could rewrite that equation because current is rate change of charge, and so this looks like epsilon minus Q over C minus delta Q over delta T times R. And that was equal to 0. And then down here, essentially by rewriting the current, you'd have like IR minus Q over C is 0, and so delta Q over delta T times R minus Q over C is 0. And the reason why I've rewritten those this way is, notice that in this case and in this case, you essentially have a term that is just a constant. It's the battery's EMF. You have a term that is, let's say, like thing. So current in this case, charge in this case, multiplied by a constant parameter. And then you have a last term that is some other constant times a rate change of the thing that you had in the second term. So these two equations look very similar. We've swapped out current for charge, but otherwise they look similar. And 2 and 2' are also very similar. We have thing and we have minus rate change of thing. Here we have thing and minus rate change of thing. Now this one, I've got these as minus Q over C and R delta Q over delta T equals 0. But remember that I can multiply everything in the equation by minus 1. And so this equation right here actually is the same basic form as the previous equation. So if I multiply all by minus 1, I end up getting like this, Q over C minus R delta Q over delta T equals 0. So again, delta I over delta T, delta Q over delta T, I, Q. So these equations and these equations look the same. We've just replaced charge with current. Therefore, we expect them to have basically the same general equation. With this caveat, in this equation for the RC circuit, we have R delta Q over delta T, and then we have Q over C. In this equation, it's I times R rather than I over R. All right, so we expect for this one right here to have a similar solution to this one right here. Both of these we would expect to have essentially an equation of the form thing as a function of time, so like Q or I as a function of time. We could call it like X as a function of time is equal to some maximum X e to the negative T over tau. But down here, tau would look like R times C. For this one, because R is in the numerator rather than the denominator, we would expect tau to be L over R. Okay, so let's write the solutions to those equations. And we'll do it in the form of like circuit type and then solution and decay time constant. So circuit types, basically we have LR circuit basically like charging, so we could call it LR1. We could call it LR circuit discharging, or LR2. We have RC circuit charging, so that would be like 1 prime, and we have RC circuit discharging, so that would be like 2 prime. Okay, so the solution here ends up being current as a function of time is the maximum current that we're going to sort of build up to times 1 minus e to the negative t over tau. This one right here, current as a function of time, is the initial current, I naught, e to the negative t over tau. Your decay time constant is this tau term, by the way. Down here, we're looking at charge, so Q of t should look like Q max times 1 minus e to the negative t over tau. And then this one right here, Q of t, we're discharging. This is your Q naught e to the negative t over tau. So what are the decay constants tau determined by? Well, tau over here would look like the inductance divided by the resistance, and that's the same for this one. So L over R. For the RC circuits, tau is RC. Now, is there anything else to be added to all of this? Yes, because all of these are in terms of either current or charge, and so we might want to put them in terms of voltage. All right, so this one right here, you can say something like voltage as a function of time is equal to whatever the EMF is times 1 minus e to the negative t over tau. That's what you're charging up to. This one right here, voltage as a function of time, is equal to V naught e to the negative t over tau. And it's worth noting that, maybe we could have another column here that relates these. So I max would look like epsilon over R. This one right here, V naught is I naught R. It's a little less informative. Down here, your Q max should look like epsilon max or epsilon C. And we could also say that like delta V max is epsilon. Okay, so this one right here, V of t, is V max times 1 minus e to the negative t over tau. This one right here, V of t, is V naught e to the negative t over tau. And so your V naught is your Q naught over C. Okay, so that basically solves all of these. I said that I would show graphs, so maybe a quick, what do these graphs look like as a reminder? So here's the graph for current versus time for the position 1 LR circuit. And it's set so that the half-life is 1 millisecond. And you can see that because at 1 millisecond we have 1, and at 2 milliseconds we're at 1.5, and at 3 we're basically at 1.75. So we're getting closer and closer to 2, which is the maximum current here. And as a quick reminder, I just referred to half-life, quarter life, eighth life. Those are related to that time constant by taking natural log. So if you want to get from time constant to half-life, you're multiplying or dividing by a natural log of 2. For quarter life, it's natural log of 4. For 1 over x life, it's natural log of x. Okay, for the discharging case, that same rule also applies. And this right here is what your discharging graph looks like. So we started at 2. After a half-life, we're at 1. After a quarter life, we're at a quarter, which is 0.5, and so on. So that's it for today's video. Thanks for watching.